In this demonstration, we're going to show you the emission spectra of elements and compounds. Here's the setup. I've got a glass tube filled with vapor. In this case, it's mercury vapor. Now I put that tube into a device that allows electricity to flow through it. That's what that black box with the white sockets is. It's just a device that allows electricity to pass through the tube. Notice that the tube is glowing. Why? Well, as electricity passes through the vapor, it excites the atoms in the vapor. Those atoms eventually have to get rid of all that energy, so they get rid of the energy by emitting light. And that's the light you're seeing coming from the tube. Now the glow is sort of bluish white, but what you don't realize is that glow is actually made up of several specific wavelengths of light. And I'm going to show you that by putting a diffraction grating in front of the camera. A diffraction grating splits up light into its individual wavelengths. And when that happens, you see something pretty remarkable. So what are you seeing through that diffraction grating? You're seeing different images of the tube, but those images are different colors. All the way to the right, there's sort of a yellow-green, sort of thin image. Then there's a thick green image. Then there's a thick blue image. And then there's a thin blue image. What are those? Those are individual wavelengths of light being emitted by the excited mercury. All right then, let's look at another tube. This is a tube of hydrogen gas. Once again, the electricity is passing through it, exciting the hydrogen atoms, and then the hydrogen atoms are decaying by emitting light. Notice that this light is a slightly different color than the light emitted by the mercury tube. That's because there are different wavelengths of light involved, and as soon as I get this diffraction grating set properly, you're going to see that. Okay, you can kind of see the wavelengths now, but the camera's going to zoom in on them here in a second. Now notice this time I've got completely different colors and a lot more of them than I had with mercury. I've got orange, red, yellow, and blue. All right, and they're all different specific wavelengths. So hydrogen gas emits individual wavelengths as well, but the individual wavelengths are completely different than those emitted by mercury gas. Results like these puzzled scientists who were trying to understand atomic structure. Why would atoms emit specific wavelengths of light when they were excited? And why would those wavelengths vary from one atom to another? Before I answer that question, let's look at another tube. This is a tube of neon gas. Notice all the wavelengths it's emitting. Niels Bohr was the first to offer an explanation as to why atoms emit individual wavelengths of light and why those wavelengths vary from atom to atom. The answer, according to him, is that the electrons in an atom are only allowed to orbit the atom in specific orbits. Each orbit has a specific energy associated with it. So when an atom absorbs energy, it absorbs energy by an electron jumping from one specific orbit to another specific orbit. Thus, an atom can only absorb a specific amount of energy, the energy that corresponds to the difference between the energy of the first orbit the electron was in and the energy of the final orbit the electron was in. In the same way, when an atom wants to get rid of energy, its electrons must decay back to a lower orbit. When they do that, they have to emit light. But once again, that light can only be of a certain energy. The energy difference between the orbit the electron started in and the orbit the electron finished in. A specific energy of light corresponds to a specific wavelength of light, which corresponds to a specific color of light. So those specific wavelengths that you're seeing are simply the result of electrons traveling from one specific orbit to another specific orbit. And that's the foundation of the Bohr model of the atom. Well, since compounds are made of elements, you would expect that if this happens to atoms, it should happen to molecules, and indeed it does. This is a tube of carbon dioxide gas. Notice the individual wavelengths being emitted once again. Since each element in each compound emits a unique pattern of individual wavelengths of light, this is a means of identifying compounds and elements. This pattern of individual wavelengths being emitted is called an emission spectrum, and the emission spectrum of each element in each compound is unique. Scientists who study stars, for example, can determine what elements and compounds exist in a star by looking at the emission spectra that come from the star.